Welcome to the Neuromodulation Podcast, presented to you by the International Neuromodulation Society. Dive into the forefront of today's emerging neuromodulation techniques, insights, and ethical and clinical applications. Subscribe now to join the multidisciplinary collaboration of medical care providers, scientists, and engineers who are part of the global conversation that's shaping the future of healthcare. Welcome to the Biostatistics Articles live reading series, presented by the International Neuromodulation Society and developed in collaboration with the Newcastle Cognition Lab at the University of Newcastle. I'm your host, Mandy Soleil, and it's a pleasure to have you here. We're pleased to offer this ongoing series of short articles explaining how to critically apprise clinically relevant literature to evaluate evidence and inform practice. The entire series of articles is available on our website at www.neuromodulation.com/biostatistics-articles, and a direct link to this article is available in the episode show notes. We've translated each article to a live episode on the Neuromodulation podcast to bring versatility and ease to your statistics learning journey. Each primer features a single topic and an example within the context of clinical neuromodulation research and practice. Upon reading and/or listening to these articles, learners will be able to understand statistical methods, their interpretation and their limitations, identify cognitive biases to avoid inadvertently misinterpreting evidence, and interpret data for a deeper understanding of clinical research to inform clinical practice. And now, I present to you Professor Konstantin Slavin, head of the Stereotactic and Functional Neurosurgery section at the University of Illinois Chicago, or UIC, and president-elect of the INS. His term as president begins September 1st, 2024. Thank you for tuning in.
The second installment of the biostatistic articles deals with how to interpret risk ratios, odds ratios, and hazard ratios. It is written by Quentin Gronau, Garston Liang, and Alexander Thorpe. There are do's and don'ts highlighted in the paper. Do's are: compare the probability of experiencing an event in two groups with the risk ratio. Compare the odds of experiencing versus not experiencing an event in two groups with the odds ratio. Compare the instantaneous rate of experiencing an event in two groups with hazard ratio. Don'ts: do not interpret odds ratio as risk ratios unless the risk of the event is low in both groups. Don't interpret hazard ratio as risk ratios. Part 1. Measuring the effectiveness of a new drug for lung cancer. The goal of many clinical studies is to understand the association between an exposure or risk factor and an outcome of disease. Suppose you are interested in investigating the effectiveness of a new drug for treating advanced lung cancer. To this end, you assign 1,000 patients to the exposure group who receive the new drug and 1,000 different patients to the control group who receive the standard chemotherapy treatment. After 1 year, 699 of the 1,000 patients who received the new drug died, and 909 of the 1,000 patients who received standard treatment died. Risk ratios, odds ratios, and hazard ratios are the three commonly reported measures that quantify how effective exactly the new drug is compared to the standard treatment. Part 2. Risk ratio. The risk ratio, also called relative risk, compares the risk of death in the exposure group who received the new drug and the control group who received standard treatment. Risk is simply a different term for probability and is consequently a number between 0 and 1. The upper part of provided figure 1a displays how to calculate the risk ratio. In the exposure group, 699 of the 1,000 patients died, so the risk of death is 699 divided by 1,000, or 0.699, or 69.9%. In the control group, 909 patients out of 1,000 patients died, so the risk of death is 909 divided by 1,000, or 0.909. or 90.9%. The risk ratio is the ratio of these two risks, 0.699 divided by 0.909 equals 0.77. This risk ratio indicates that the risk of death for patients who receive the new drug is 77 of 100ths of the risk of death for patients who received standard treatment. A risk ratio smaller than 1 indicates that the drug decreases the risk of death. A risk ratio larger than 1 would indicate that it increases risk of death. The risk ratio of 1 would indicate no difference. The figure 1 has two panels. One panel A indicates risk ratio and odds ratio formulas with risk exposure group divided by risk control group, and the risk ratio is a result of this division, and the odds ratio, which is a ratio between odds exposure group and odds in the control group, and that's what odds ratio is. Part B indicate percentage of patients surviving in the exposure and the control group over time. Panel C shows the relation between the risk ratio and odds ratio for 4 levels of risk in the control group. Part 3, odds ratio. Another common measure are odds ratios. Risk ratios are easier to interpret than odds ratios. However, correctly interpreting odds ratios is important, as well as since they are commonly reported, for instance, in the context of logistic regression. Instead of comparing the risk in the exposure and control group, an odds ratio compares the odds of death versus survival in each of these groups. That is, the number of patients dying versus the number of patients surviving. The lower part of the figure 1 displays how to calculate the odds ratio. In the exposure group, the odds are 699 divided by 1000 minus 699, meaning 699 divided by 301, which is 2.32. In the control group, the odds are 909 divided by 1000 minus 909, which equals to 909 divided by 91, which in turns equals 9.99. The odds ratio is the ratio of these two odds, 2.32 divided by 9.99, which is 0.23. This odds ratio indicates that the odds of death for patients who receive the new drug is 0.23 of the odds of death for patients who receive standard treatment. An odds ratio smaller than 1 indicates that the drug decreases the odds of death. Odds ratio larger than 1 would indicate that it increases the odds of death. The odds ratio of 1 would indicate no difference. Part 4. Hazard ratio. Risk ratios and odds ratios assess the effect of an exposure or risk factor on an outcome or disease at a fixed point in time, in this case after 1 year. However, what if one had decided to assess the effectiveness of the new drug after 3 years instead? In this case, one might obtain a different risk ratio and odds ratio, thus different conclusions. Hazard ratio addresses the issue. Instead of comparing the risks or odds in the exposure and control group at a particular point of time, hazard ratios compare the hazard, the instantaneous event rate, which can be thought as a probability of dying in the next one time unit given one has survived so far. Consider a hypothetical example in figure 1b where plots the percentage of patients surviving in the exposure and control group over time. For this hypothetical example, the hazard in both groups is constant over time and can be thought of as an answer to the question, given I have survived until now, what is the probability that I will die within the next months? Suppose the hazard of dying in the treatment group is 0.1 and the hazard of dying in the control group is 0.2. The hazard ratio in the ratio of these two hazards is 0.1 divided by 0.2, which equals 0.5. This hazard ratio indicates that the hazard of death for patients who receive the drug is 1/2 of the hazard of death for patients who receive standard treatment. Hazard ratio smaller than 1 indicates that the drug decreases the hazard of death. The hazard ratio larger than 1 would indicate it increases the hazard of death. A hazard ratio of 1 would indicate no difference. Part 5. Common misconceptions. There are 2 common misconceptions one should be aware of. Misconception 1. Interpreting odds ratios as risk ratios. Odds ratios are often interpreted in the same way as risk ratios. In general, this is incorrect and should be avoided. However, in specific scenarios, the odds ratio approximates the risk ratio and can thus be interpreted as such. Specifically, it can be mathematically shown that odds approximate the risk when the risk is close to 0. Thus, if the risk both in the exposure and control group is close to 0, the odds ratio approximates the relative risk. This is known as a rare disease assumption. The figure 1c plots the relation between relative risk and odds ratio by varying the risk in the exposure group from close to 0 to close to 1 at 4 different risks in the control group. The figure corroborates that odds ratio approximates the relative risk for risk values close to 0. The figure also highlights that the odds ratios are in general further away from 1 than the risk ratios. Therefore, if one incorrectly interprets the odds ratio as a risk ratio, one will overstate the effect. Misconception 2. Interpreting hazard ratios as risk ratios. The hazard ratio is not the same as a risk ratio. The easiest way to remember that a hazard ratio cannot be the same as a risk ratio is to recall that no one is immortal. So eventually 100% of the patients in the exposure and control group will die. Therefore, after enough time has passed, the risk of death in each group, and therefore also the relative risk, will be close to 1. However, the hazard ratio does not necessarily need to converge to 1 over time, since a hazard in each group is the probability of dying in the next one time until given one has not died so far. Part 6. Further reading. 3 papers recommended here are one by George and colleagues in 2020, published in Curious, another one by Sashegi and Ferry, published in The Oncologist in 2017, and the third one is by Cummings, published in 2009 in Archives of Pediatrics and Adolescent Medicine. Thank you.